So we're now going to talk about the applyAllSplit model of programming the Java fork join framework. And this particular method uses recursive decomposition to disperse the tasks to the worker threads in the pool that we pass in as the parameter here. So again, the overall logic is the same as for applyAllIter, which we looked at before. We have an op, which is a function. We're going to apply that op to all the items by recursively splitting using fork join methods. And the signature is the same as before. We pass in a list, we pass in an op, we pass in the fork join pool, but the implementation is quite different. What we have now is we have a nested class called splitter task. And splitter task extends recursive task. And as the name might suggest, and as the animated GIF at the bottom also indicates, we're going to recursively partition the list and then keep doing this and running them in fork join tasks. So this will actually split up the input in a very nice, even way, thereby making work stealing much lower, but there's a little cost because we have more copying and we have a little bit more method calls. This particular use case is very ideal for the fork join framework. We're splitting things in half. As you'll see, it takes very little effort to do that. So it's kind of the model citizen case for how to do these kinds of things with fork join framework. As you can see, again, we're going to use the invoke method. This is the method that's used by non-fork join task clients. And it's going to kind of kick things off, start the ball rolling as it were. And we're going to create a new splitter task that will start with the entire list. So let's go ahead and take a look and see what splitter task looks like. As I said before, splitter task extends recursive task, and we're going to use a list or sublist for each of the pieces. We're going to define a list, and the list is then going to be initialized in the constructor. And again, remember Java's reference semantics, so we're not actually making a copy of the list, we're just passing in a reference to it. So that initially, we're going to have a field, mlist, that will reference the entire list. Here's the compute method. This is used to recursively perform the computations in parallel on subsets of the overall list. And we'll start out with the basis case for the recursion, which says if the size of the list is less than or equal to 0, it should be equal to 1, actually. I'm sorry, less than or equal to 1. It should be 1 at this point. We make ourselves a new array list, and then we're going to iterate through all the elements in the list, which there typically is just one of them, and we're going to add the result of applying the operation to that element and stick that in that list. So again, that's the base case of the recursion, and then we return this new list, which should have one element in it, which has been computed with the result. So that's the base case of the recursion. Here's the other part of our recursive compute algorithm. First thing we do is we determine the midpoint in the list, which is very easy because we just take the size of the list and divide it by 2. Nothing could be easier than that. That's our midpoint. And then what we're going to do is we're going to recursively and evenly partition the list, kind of like snapping a candy bar in half, if you will, to be fair, to have equal size for everybody. So what we do is we make ourselves a new list, and this is going to be a fork join task of list, and we're going to make a new splitter task, and that splitter task is going to go from the beginning of the list up to the midpoint. So that's the left-hand side task, the left task, and we're going to go ahead and fork that. So that'll be arranged to run in parallel in the fork join pool. And what we're going to do in this case, is, as you can see, is we're going to be pushing larger partitions onto the deck before the smaller ones. And as we've talked about before, that helps with work stealing because you're always stealing bigger elements at the end of somebody else's deck. We then go ahead and we create an updated list field, mlist field, that will be from the midpoint to the end. So this is the second half of the list. And that's going to be basically the right-hand side of this. And we're going to end up computing or calling ourselves compute on that right-hand side. And the reason we do that is we want to minimize context switching. So we're going to fork off a new task to run on the left-hand part of the list, and then we're going to compute the right-hand part ourselves. So compute is next called, and that will block. Meanwhile, we've forked the left-hand side. That will then be run typically in a different thread that's been stolen usually. And then after we're finished computing, we, the parent in this model, call join on the left-hand task, waiting for its result to come back. So we're going to be joining with the left-hand side, and that will end up getting our left-hand side result back. And then we add the right-hand side result, which we computed in our thread, to the left-hand side that was computed in some other thread, and that joins everything back together again. And then we go ahead and we return that joined result. So it's starting with things split in half, and then we join them back together again, and all the pieces are put together. Now, keep in mind that there's going to be some data copying here because these are implemented as an array list, and so we're going to have to copy stuff. So there is some overhead of copying. Now, what about this implementation? Well, it's a little harder to program because it's recursive, and it's also a little harder to understand because it's recursive. Although once you kind of get the basic model, it's kind of paint by numbers because it always looks pretty much the same. So one thing that would be helpful here, as was the case with the applyAllIter method we looked at earlier, is to kind of take a look at how to visualize this. And so let's take a look at how we could visualize the usage of this particular approach. So in this particular case, we're going to call fork join pool invoke, creating the new splitter task with the initial list, the entire list at the beginning. That again is how we get the non-fork join task clients to give a task into the fork join pool, into its queue. And then at that point, things get interesting. And what happens is, because of the fact we're using recursion, we're going to very nicely spread out the processing of these subparts across all the threads in the pool. So one of the consequences of this, as we'll see when we look later at how it all performs, and we count the amount of work stealing, the amount of work stealing in this model is very, very low relative to the amount of work stealing in the applyAllIter model. And that's because we're partitioning things up in such a way where they're splitting by the recursion, and this is being done in different threads, and therefore it much more evenly splits and decomposes the various parts across the threads in the thread pool. So the consequence is work stealing overhead is lower. However, copying overhead, because we have to copy these elements and put them back in lists, and method call overhead, because we're doing all these recursive calls, is higher. So it really comes down to what's more expensive, copying and method calls versus work stealing. And we'll actually be able to answer that question here shortly. Note how the forked subtask and compute subtasks will have the potential, or actually will, on a multi-core processor, run in parallel. And also note again how the compute call here runs in the same task as the parent in order to optimize the performance of the system. So the nice thing about this is we have a much more balanced tree of join calls, which also scales better than the applyAllIter approach, because we're doing these things in different threads, and so there's less contention and just works more evenly. So that's the end of the applyAllSplit analysis. So that's the second model that we're going to see here. And of course, as it turns out, there's yet other ways to further improve the way in which all these pieces fit together. And we'll take a look at that in the next example.